This is chapter 2 where we are discussing strain. This is the third session involving strain. Here we will discuss statically indeterminate axially loaded structures. This is the overall picture of the first 4 chapters. We think it is helpful to switch to this overall picture before we deal with the session at hand, which is this session. This is the last main session in chapter 2, where we are dealing with strain and the relationship between strain and stress. Here we will discuss statically indeterminate structures of bodies subjected to axial loading. Till now, we have dealt with statically determinate structures only. Hence, we could use equation of statics to find the external reactions acting on a structure. Once we had the external reactions, we could find the internal forces in members. Generally, with any type of loading applied to a structure, if the external reactions cannot be found using equation of statics, then the structure is statically indeterminate. Here, the discussion will be limited to statically indeterminate structures subjected to axial loading only. Later on, we will deal with statically indeterminate structures with relation to torque, relation to bending moment, etc. So let us start by discussing the analysis procedure of statically determinate structures. With statically determinate structures, using the equations of equilibrium, we can find out the external reactions acting on the structure. Thus, we can find out the forces acting in members. Hooke's law gives a relation between stresses and strains. From the relation of stress and strain, we can find force displacement relations. Using the equations of equilibrium, we have found the forces in the members, and using force displacement relations, we can find the displacement of the members. Now let us look at statically indeterminate structures. In such structures, the equation of statics are not enough to find out the external reactions acting on the structure. Hence, equation of compatibility is used to find additional relations. Equations of compatibility are relations between displacements. Using the displacement force relations that I've just mentioned, we can turn the relations between displacement to relation between forces. With this relation between forces and the equilibrium equations, we have enough equations to solve for the unknowns. This way, we can find all the reactions. Once we have the forces, we can find out all the displacements. It needs to be pointed out that equations of equilibrium do not use any material property, but compatibility relations do use material property. As a result, the forces found out do depend on the material. We look at two simple cases, a determinate case and an indeterminate case. A here is a determinate case. AB is subjected to a compressive force and there is a reaction at B. Rb is the only reaction force, and Rb is equal to P, which we find out using statics. Having found out the force, we can use force displacement relation to find out the displacement of AB. Thus, we use the equation delta is equal to PL by EA to find out delta AB. In B, we see in case of a bar with two different cross sections held between two walls at A and B and subjected to a force P at C. So there are two reactions at A and B, RA and RP. But there's only one equation from statics, that is RA plus RP will be equal to P. We need another relation between RA and RP to solve for the values of RA and RP. Since A and B are fixed, the force P will cause AC to extend and CB to be compressed by the same amount. So this is a relation of geometric compatibility. So delta AC has to be equal to delta BC. This is a relation of displacement, which we can turn using force displacement relations into equation of forces. We use the relation delta is equal to PL by EA on both sides. So this gives a second equation between RA and RP. And we can find the values of RA and RP. Once we have found the values of RA and RP, we can find delta AC and delta BC, the displacements. The force displacement equations are also called constitutive equations, since they relate to the physical properties of the structure. The previous example, we dealt with the deformations added up to zero. Among the different types of problems we will deal with, the deformations may add up to zero. They may be equal to each other. They may add up to a finite value, or they may be in proportion of each other. We'll deal with the case where the deformation is equal next. After that, we'll deal with two cases where we will use the proportion of deformations based on geometry. We have dealt with cases where we have used the relation between deformation based on geometry in statically determinate structures. However, in statically determinate structures, we initially found the deformation at certain points. We were then asked to find the deformation at some other point. We used the geometry of the structure to find out the deformation in these new points. In statically indeterminate structures, the use of geometry is different. To start with, we do not know the external reactions acting on the structure. We use the relations between deformations based on geometry to find out the external reactions acting on the structure. After we have found out the external reactions, we proceed to analyze the structure in a normal way. We now consider this example. We have a steel rod and an aluminum tube, and a load is acting as shown. There are two unknown forces, the force in the steel rod and the aluminum tube. These two forces add up to P. So from statics, we get the first equation. For the second equation, we see that the deformation of the steel rod and the aluminum tube has to be equal. So delta S is equal to delta AL. We convert this equation of displacement into equation involving forces by using force displacement formula. So we get the second relationship. This is the second equation involving forces. From equation 1 and 2, we get the value of PS and PAL. Substituting PAL in this portion of this expression, we get delta AL, which is also delta S. Here we have a beam ABDF, which is hinged at A and hung by two wires at BC and DE. It is subjected to a force P at F. We can see that there are three unknowns here: force in DE, force in BC, and the reaction at A. There are two equations of equilibrium. So we can take moment about A and we can sum up forces in the vertical direction. We don't need the reaction at A and we don't use the equation summation Fy is equal to 0. So we are left with two unknowns, the forces in BC and DE, and one equation of statics, which is the moment about A. We need another equation from compatibility, and ABDF deflects as a straight line, and since the lengths are the same, the deflection DE would be 2/3 the deflection of M, and deflection of BC would be 1/3 the deflection of F. So here we have the first relationship from equilibrium, and from compatibility, the second relation. This relation between deflection can be changed into a relation of forces by using deflection force equations. So we have used delta SPL by EA. One would note that the lengths of these two wires are different. So we get a relation of between RT and RP here. So now we have two relations between RT and RP, and we can find RT in terms of P. Knowing the value of P, we can find the value of RT. Now using delta SPL by EA, we can find delta TE. Once we have delta TE, the deflection at F is 1.5 times delta TE. So we can get the deflection at F. So here we have the second problem, which is similar to the first problem. The bar ABC is hung by three wires, and a force P is applied at B. We have three unknowns here, the forces in the three wires, and we have two equations of statics, kinetic moment about A and C. And the third relation we have to find it from compatibility. So A, B, C, B being a bar, it will deflect in this manner. The lengths of AP and BC being the same, if the difference between del B and del C is del 1, then the difference between del A and del B will also be del 1. So here we have taken moments about the 2 points, and we have a relation between RP and RA and a relation between RP and RC. And from compatibility, we have del A minus del B is equal to del B minus del C, which using deflection force relation turns into a relation of forces of RP, RA, and RC. Now using equation 5 and equation 1, we can multiply the equation, one of the equation to eliminate RP, and then we'll get a relation between RA and RC, which we here have as equation 6. Similarly, with equation 5 and equation 2, we can eliminate RP, and we can have a relation between RA and RC, which we have as equation 7. Using the two simultaneous equations, we can find RC. Now, substituting RC in equation 6, we find RA, and with RA known, substituting that in equation 1, we can find RP. The cases of statically indeterminate structures that we have dealt with till now can be considered as normal cases. Apart from these, there are special cases involving thermal strain, misfits, and pre-strain. Among other special cases are settlement in structures. In statically determinate cases, thermal strains, misfits, or pre-strains do not cause forces generally. However, in statically indeterminate cases, even without external loads, thermal strains, misfits, and pre-strain can cause forces. These forces are in equilibrium. As previously, among cases, deformations may add up to 0, they may be equal, they may add up to some finite value, or they may be in proportion of each other. We consider a thermal strain case here. A body whose temperature is raised will expand in all directions. The coefficient of thermal expansion is the expansion per unit length and unit increase in temperature. The coefficient of thermal expansion is denoted by alpha. Hence, if a bar is of length L and its temperature is increased by del T, then the increase in length would be alpha del T into L. Like the equation between force and displacement is called a force displacement equation, the relation between temperature and displacement is called a temperature displacement relation. The case here consists of a steel bar and a copper bar. A and C are fixed and the temperature has been raised by 75 degrees. We need to find the forces at A and C. We understand this problem by considering that the end A is released. If the end A is released, then with the increase of temperature, the whole bar will increase in length. We say the increase in length is del temperature. Then we apply a force P so that this bar returns to the original length. Then force P is equal to Ra, which will be equal to Rc, and delta temperature is equal to delta force. We find out the increase in length of the bar due to temperature first. The relations as earlier mentioned are called temperature displacement relation. So for steel, we have the coefficient of expansion multiplied by the increase in temperature and length. And for copper, we have the coefficient of expansion and temperature and length. And we add these two up, get the total increase due to temperature. We next find the decrease in length due to force. Now there are two parts here. The one is the copper and the other is the steel. So they have different areas and different Young's modulus and length. So we need to find the increase in length individually and add them. We find the increase in length using delta is PL by EA, and the total length would be the delta force. Earlier we have obtained the delta temperature, so we equate delta force and delta temperature, from which we find P. Now P is also Ra and Rc. This is another example of thermal strain. The initial temperature of the arrangement is given. The temperature of the arrangement is raised, but we are not told how much the temperature is raised. Due to the raising of temperature, it is mentioned that the stress in steel attains a certain value. So we are asked to find the increase in temperature and the increase in the length of the steel portion. The problem can be seen as the reverse of the previous problem, since we are asked to find a temperature increase. The problem can be understood in a similar way to the previous problem. With the increase in temperature, both the steel portion and the bronze portion increases. Initially consider that there's no support at A, so they can freely increase in length. Then consider that force Ra has been applied, and the force, due to the force, the bronze and the steel portion reverts back to this line. This force causes a stress in steel, which is given. So multiplying the area of steel by the stress, we get Ra and Rb. So that covers the equation of statics. We'll now look at the equation of compatibility. With compatibility, we mentioned that there are different cases, and one of the cases are a deflection are equal, or deflection add up to 0, or deflection add up to a finite value. So in this case, the deflections add up to a finite value, which is 0.8. So with temperature, the bar will increase in size, and with the force will decrease the bar in size, but not totally, so that there is a gap of 0.8 millimeter. Now, this is an equation of delta, so we can use displacement force equation and displacement temperature relations in this equation. We note the force, so we substitute delta is PL by EA, and delta L is equal to alpha del T into L for the two different portions, from which we get the increase in temperature. The initial temperature was given, so adding that up, we get the total temperature. Since we now know the increase in temperature, we can find how much the steel has extended. So we can use the increase in length due to temperature and subtract it from the increase in length or decrease in length due to force. So we find the total increase in length and the total length. Statically indeterminate problems include misfits and restraints. Sometimes structural assemblies do not have the specification originally intended. This is due to error. So some members may be incrementally smaller or larger than specifications mentioned. This is called a misfit. If the assembly is indeterminate, then this can induce inbuilt stresses in structures. On the other hand, we may deliberately introduce initial strain in structures. Such structures can have strain and stress without loading. As an example, consider this assembly. This is a bolt, this is a bolt head, and this is a sleeve. The pitch of the bolt is P, and the bolt is given n turns. So if there was no sleeve, then the bolt would reduce by a length np. Now let us look at forces first. This diagram is the equilibrium diagram of the bolt head. Since we have tried to shorten the bolt, it pulls the bolt head with a force. However, the sleeve prevents this, and there's a force in the opposite direction. The bolt head is in equilibrium due to these two forces. Since there's no other forces, these two forces would be equal and opposite. There will be reaction forces on this left part of the structure without the bolt head by the bolt head, as shown here. So these two are action-reaction forces, and these two also are action-reaction forces. Due to the forces of the bolt head, the sleeve is being compressed and the bolt is being extended. We have earlier seen that PS is equal to PB. Now let us look at deformation. This length is the free length of the bolt. However, the bolt will increase in length due to the forces caused by the sleeve. And this whole length is the free length of the sleeve. However, the sleeve will reduce by a certain length due to the forces caused by the bolt. In the end, the length of the bolt and the sleeve must be the same due to the bolt head. So, in the end, they occupy an intermediate position as shown. The deformation equation can be written as delta B plus delta S is equal to NP. We can write in terms of force displacement equations. Here P is both PS and PB. And from this expression, we can find out P. We can then find out the reduction in length of the sleeve. Here we consider a pre-stressed beam. This is an arrangement where there are two steel wires and is attached to two ends as shown. We apply a force F to this arrangement, and as such there's an extension delta SF of the wires. We then pour concrete in between the ends and remove the force F. Without the force F, the wire would have reverted to its original position. But it is prevented by the concrete. After removal of the force F, the concrete is compressed due to the wire, and the wire is extended due to the concrete. The final position of the pre-stressed beam is somewhere between the initial length of the structure and the length after application of the force F. Since the force F has been removed now, there are only two forces acting. One is the force due to the steel wire on the concrete, and another is the force on the steel wire due to the concrete. These forces are in equilibrium, so they form the static equilibrium. Here we can see that due to the concrete, the wire has extended. So that is given by del SP. And due to the wire, the concrete has contracted, which is shown as del CP. And these two add up to del SF, which was the original extension of the wire due to the force F. So this gives us the relation of reflection or deformation. Now substituting the force displacement relation, we get this equation. Notice that this is F and these are P. From this equation we can get P, that is the force between the concrete and the steel, and we can get the stresses in concrete and steel and the final deflection. We earlier discussed about misfits. So in some structures, components are not built exactly to specifications, and there can be small imperfections. So the length of a component may be smaller or larger. Here we have an aluminum tube and a steel rod. There's a cap to which a load has been applied. As we see, there's a gap between the steel rod and the aluminum tube. The magnitude of the load is considered to be such that this gap gets closed when the load is applied. From statics, we see that the force in the aluminum tube and the force in the steel rod must be equal to P. So this is the equation that we get from statics. From deformation, we see that the compression of the steel rod has to be 0.04 millimeter more than the compression of the aluminum tube. So delta S is equal to delta AL plus 0.04. So in this equation, we substitute the force and displacement equations, and we get this expression from which we get another equation of PS and PAL. From equation 1 and equation 2, we can find PS and PL, PAL, and then putting back in this equation, we can find the deflection of the steel and aluminum.